Well, hello everybody, Dave here, and welcome to your third lesson in the unit on uniform circular motion and gravitation. And now that we've dealt with the basics of circular motion and we played around with some more complex applications, it's time to talk about the other end of this unit, and that's the idea of gravitation. And it's important to recognize that until now we have made an assumption that we've always been pretty close to the surface of the Earth. And because of that, there are some quantities that we can simply say are constant, such as the acceleration due to gravity. But we know that as we move farther away from the surface or farther away from the center of mass, then this gravitational field strength is actually going to change. And this is going to be the lesson on that. So to begin our discussion, we have to recognize one truth, that we're really talking about Newton's third law in most of the questions that we're dealing with. And the reason that is because if we talk about the moon orbiting around the Earth, and we talk about the force of gravity between the Earth and the moon, then what we have to understand is that the gravitational force exerted on the Earth by the moon has to be the same as the gravitational force exerted on the moon by the Earth. This is an action-reaction pair. It's the exact same thing for us standing on the surface. It's weird to think about it, but if you talk about the Earth exerting a force downwards on you, you could also consider it that you are actually exerting an upward force on the Earth itself. It's an action-reaction pair, and this is an important thing to recognize when we're dealing with gravitation. Now, the derivation of gravitation is a pretty tricky one. And the first thing we have to understand is that when we're dealing with fields, and you will deal with multiple fields in physics. Specifically in this course, you're going to deal with gravitational fields, electric fields, magnetic fields. You're going to notice that there's going to be this similarity in the formatting of the equations themselves. And many of them are going to relate to a 1 over r squared relationship. And the question is, why is that? Well, the first thing we have to understand is that the intensity of a field is based upon the strength of generation divided by the area of effect. And so what do I mean by that? Well, if we're talking about gravitation, then we have this quantity, this maximum strength that the Earth can generate that's going to create its gravitational field. And it was Sir Isaac Newton that came up with the idea that the strength of the Earth was 4 pi gm. Now, I don't know how to get that, and I'm happy to listen to anybody who wants to talk me through it, but this is why Isaac Newton is who he is. But if we talk about the area argument, now this is something that we can play with. Because if we look at our 3 different cases when we are 1 radius away, 2 radii away, and 3 radii away, look what's happening to the area of influence over those distances. If we look at the intensity calculation for the first radii, well, that's just S divided by, well, since it's spherical in nature, the surface area of a sphere is 4 pi r squared. And so we would get S over 4 pi r squared. Well, look what happens when we go 2 radii away. Well, 2r squared is actually 4r squared, and that's why there's that 4 there. But what's happened is the strength didn't change. It can only generate the field at the strength that it can, but the distance away from where this center of mass is determining that you're going to feel an intensity that's a quarter less than the intensity when you are 1 radii away. And you can see that at the third distance away, because of the surface area, the intensity of the gravitational field strength at that distance is actually 1/9 of what it was when you were only 1 radii away. So this should make a lot of sense now, because we have these concentric spheres that are permeating out, and as a result, because the strength of generation isn't changing, the intensity felt is going to decrease at a rate of 1 over r squared, because there is more area of influence that it has to have. And so what we end up with is intensity is this strength, which Newton found is 4 pi gm, over the area, which is 4 pi r squared, where r is whatever it is. And once the 4 pi's cancel, you get this gm over r squared. And folks, this is what we call our gravitational field strength. There will be similar derivations that give you the electric field strength, and we'll save that for a different day. But this only applies to point sources that radiate outwardly in concentric spheres. If there's any sort of different shape involved, then it's a different geometry, which means it's a different discussion. But that's a really neat, straightforward derivation that gets us there. Now, This value of G is something that can actually be experimentally found, and it was Cavendish that found it back in 1798. And the way he did it is he got two sets of spheres of known masses, and they put them a certain distance apart. And what he did is he attached a mirror to a torsion balance, and basically what that is we can actually see very accurately how much the string is being twisted, and because of that we can actually figure out how much force had to be applied. And there's some difficult math at that point, but what you can come up with is a fairly accurate representation of this universal gravitational constant. And so that's an important thing to recognize, is we had this constant that needed to be found, and Cavendish actually was able to find it, which makes a lot of this math still applicable even today. So since we have an acceleration, and we remember that we used to calculate weight with mg when we were just at the surface, now we can find what Fg is at any gravitational field strength simply by plugging in our gravitational field strength equation of gm over r squared. And what we get here is Newton's universal law of gravitation, which is gmm over r squared. This is considered his unofficial fourth law because it is a result of his laws, and it's an important element to understand that this equation is still very much useful in understanding astrophysics and the motion of bodies and things like that. Certainly a simplification, there is some different things going on, but for circular paths, this is still the gold standard. Our value of G, by the way, is 6.67 times 10 to the minus 11 Newton meter squared per second squared. You will absolutely be given that always, at least in my class. Other people, it's up to them, but certainly not a horrible thing to memorize or to program into your calculator. Okay, let's do an example problem, and this is a different example problem. And the reason that I say it's different is because you're not going to just simply plug and chug. A satellite weighs 9,000 newtons on Earth's surface. How much does it weigh if the mass is tripled and its orbital radius is doubled? So what people classically want to do with this is go, oh, okay, well, it weighs that on the surface, so I'll figure out its mass by dividing by 9.8, and then I'll plug it in at a certain radius, which I'll multiply. Oh, hey, Dave, what's the radius of the Earth? And then they'll go and they'll crunch and get a number like that. And the thing about that bothers me isn't the ability to solve the problem, it's the ability not to think a little bit out of the box. And what do I mean by that? Well, we know that weight is equivalent to the idea of the force of gravity. So we know this 9,000 is going to play an important role. But what I'd rather find out is what relationship exists between the new weight and the old weight. And for that, I'm going to go to Newton's universal law of gravitation. And you'll notice that what I'm doing this time is I'm substituting in that I'm going to say that R2 is double R1, which is what the question said, and M2 is triple M1, which is what the question said. When you substitute those quantities in, don't forget to square that 2, you end up with 3 over 4 GM-M1 over R1 squared. Well, look, we've already defined at the beginning of the question that Fg1, which is 9,000 newtons, is GM-M1 over R1 squared. And what that means is we don't need to go through that process of finding constants of the Earth and calculating masses and rounding errors and things like that. You can simply find this relationship that tells us that Fg2 is 3/4 of Fg1, and you can simply multiply 9,000 by 0.75 to give you Fg2 as 6,750 newtons. So I encourage you, don't always rely on constants to get you the answers. If the constants aren't there, that means there's another way to go. And if there's an analytical approach to it, which is what this is called, analytical reasoning, then I would encourage you strongly to go at it like that. Now we're going to get into how circular motion plays a role in this. And for that, we have to get into the idea of orbiting satellites. And this is just a picture that I found from NASA that's actually showing all of the objects orbiting the Earth right now, and you can see that it's a pretty busy space out there. And so you'll notice that there is some obvious patterns associated here. Right near Earth, there's a huge clump, and then you see that very well-defined circle that's a good distance away. And the interesting thing about that is, why does that exist? It seems like it's random otherwise, but there is this nice uniform circle. And the reason for that comes from understanding what force is responsible for that circular path. And so when we're dealing with orbits, what we're talking about is that the tangential speed is high enough so that satellite doesn't fall to the Earth, but it also doesn't fly away from the Earth. It maintains this circular path. And so when we're dealing with that, what we're talking about then is different types of orbits. And we'll get into how to define those different types of orbits in a minute. So the first and most important case is this idea of a circular path. And so in order for it to be a circular path, that means that all of the things that we learned about centripetal motion have to be satisfied by this motion. So what do we mean? Well, that means that Fc in this case is going to be equivalent to Fg. And so remember that the big question we had to ask ourselves is, what is the force responsible for it maintaining its path? Well, in an orbital path, in a circular case, the force responsible for maintaining its path is, in fact, the force of gravity. And we know that that's always equivalent to mv squared over r because that's centripetal force. But instead of using Fg as mg, we're going to use Fg as gmm over r squared. And you'll notice one important thing. The mass of the object orbiting actually cancels out. And that's an important thing to note, because what that means is the same speed that will have an object orbit at a distance r from the center of mass is going to be the same speed if that object is twice as massive, 10 times as massive. That the getting it up there is going to be something, but once it's up there, so long as it maintains this speed, it will also maintain that distance away from the center of mass, or vice versa. And so this is a very poignant equation in that it gives you a pretty clear indication that what matters here the most is the gravitational field strength generated by the Earth itself. So we can also redefine energy because we're dealing with radial motions. And you'll remember that when we talked about circular motion, that we always talked about it in terms of centripetal acceleration pointing in or pointing away. And even though we're dealing with radial motion, we still have an orbital speed, which means we have a kinetic energy. So it's important to recognize that there's still going to be kinetic energy if the object is orbiting around the Earth. But radially, there is no initial speed, so there's also a whole bunch of potential energy because we're a certain distance away from the surface, or more importantly, from the center of mass. And so if we want to find the work required to move it radially from one position to another, then we're going to use our definition of work that we've always used, which is our change in energy. But in this case, we're going to talk about the applied force. Well, the applied force when we're dealing with gravitation is, not surprisingly, gravitation. And instead of defining d as a linear distance, we're going to label d as the distance radially from the center to the object, which is just r. And because of that, one of the r's cancel, and what we get is this equation for potential energy of negative gmm over r. Now you'll notice that negative sign, and what does that represent? Well, you can see in the derivation that we showed that the final potential energy is equal to 0, and that's when it's finally met our zero potential line, and that's fine. But that negative sign represents the fact that energy has to be released, and the reason that energy has to be released is because gravitation is always attractive. And so that negative sign, it's important to recognize in physics that negative signs aren't used in the same way that they're used in math classes. So that negative sign really denotes direction of transfer. And in this case, because it is always attractive, the potential energy is always decreasing because it's moving towards. It is actually decreasing in height. To do positive work on this would be to move it up in height, and that's a different argument by itself, because that means that there would have to be some applied force that isn't just gravitation to move it from height A to height B. That limitation that r has to be greater than or equal to the r of the Earth is because once you're below the surface of the Earth, some things change. And the equation for gravitation that we have doesn't actually follow anymore because now we have this new variable of mass above our heads to consider as well. That's something that I would discuss in class, and we'll save that for another day. So the second example now deals with a type of question that you're going to see quite often, and that's the idea of an asteroid coming in from forever away. And so they talk about this in different ways, but generally the wording looks like this. An asteroid with mass huge comes from deep space, effectively from infinity, and falls towards the Earth. Cool. So it's moving straight towards the Earth. Awesome. Find the change of potential energy and the work done by gravity when it reaches a point 4 times 10 to the 8 meters from the center of the Earth, and then calculate the asteroid's speed at that point. So to solve this, we first have to try and understand what this effectively from infinity thing means. And what it means is basically that you are so far away from the Earth that there is no discernible interactions between you. What that means is there is no potential energy present. We can show that mathematically with an infinity sign in the denominator there, but it's really even more simple than that. It's just the fact that you are so far away that you are not considered to be part of Earth's system, so there is no gravitational potential energy between you because there are no interactions to begin with. So if you take a look at the derivation here, I've done the classics, I've factored out the negative GMM, I've substituted in the values, and I've gotten the answer of negative 9.97 times 10 to the 14 joules. To no surprise, the energy is being released because it's being converted into kinetic energy, as it were. This also means, though, and this is something that you're going to have to get used to later on in the course, that this is the work being done on the object. If we're talking about the work being done by gravity, well, gravity is actually doing 9.97 times 10 to the 14 joules of work to move this object from one point to another. This whole on or by thing is something that's going to come up a lot, certainly not within the realms of gravitation, but it's something to think about moving forward in the course. The third question now is, what is the asteroid's speed at that point? Well, this is a conservation of energy question. We're not told about anything to do with friction or energy loss. So we simply know that the initial energy and the final energy is the same. We know that the loss in potential is the gain in kinetic. We know what our equation for kinetic energy is, and from that we can get our answer of 1.41 times 10 to the 3 meters per second. That is what we call fast, especially for a rock that huge. Earth would be in trouble. And so this is the classic asteroid type question that is tracking its motion from before it's ever part of the Earth system to just before it hits and everything in between. So now with this information, we can actually derive an equation to determine the speed of any falling object falling from any given height. And what we'll do is we'll summarize this by saying that the initial distance is some final distance r plus h, whatever the initial value was, to a final distance r. And you can see that we go through the conservation of energy just like we would before, but this time we solve for Vf as if all of this energy were being transferred into kinetic energy. And when you see this, this is a equation that can give you the final speed at any distance away. And so again, it is very much the same derivation that you did in the previous question, except in this case, we're just not putting in an initial height of infinity. We're putting in an initial height of, who knows? It can be whatever we want. But from that, we can begin to play around with our limiting cases. So if we go back to our original case of the object is initially stationary and is really far away, well, that really far away is going to be that 1 over r plus h turns into 1 over infinity, which we've already said goes to 0. And what we get is a final speed of the square root of 2gm over r. But if we instead decide that we want to deal with the motion where instead of it falling towards the Earth, it is actually being projected from the Earth, well, guess what? Conservation of energy would tell us that it is the exact same equation. That if all this energy initially was converted into the final speed, then conversely, to get it to escape, we're going to have to go ahead and have the exact same speed to get us out. So the important part about escape speed is understanding that when an object reaches a distance so far away that it is no longer considered interacting with the Earth. So remember that whole gravitational potential energy argument and how it is so far away that it's no longer part of it. The other argument too is that it is so far away that it has no additional energy to be converted. That again is another statement of what escape speed means. But that's the point of escape speed, is the fact that it is launched at a speed that it will just keep traveling so that it eventually gets so far away that it is no longer considered part of that system, but not any further. So what does this mean? Well, this means that there are some special cases now that we can talk about. The first one is this idea of a geosynchronous orbit. And when we're talking about geosynchronous orbits, all we mean is that the satellite is going to hover above our heads the whole time. It's not going to orbit faster and do circles. It's going to travel along with the rotation of the Earth. And so relative to us, it would look like it's just hovering. And so all that means is that the period of the orbiting satellite would be 24 hours. We have a distance that's going to be some height above the surface of the Earth. So in our case, r is going to be equal that height plus the radius of the Earth. Watch out for words like altitude or distance above the surface, because that always means that you have to also add in the radius of the Earth as well. But you'll notice again that we have an equation for geosynchronous orbits that is independent of the mass of the satellite. And so this is all derived from stuff that we've already played with in this unit. And so again, I would leave that to you to derive yourself. But based upon all of these different speeds, there's got to be something going on when it comes to the shape of the orbit based upon the speed that we have. And so there's essentially three speeds that we're talking about. We're talking about the circular orbital speed, we're talking about the orbital speed, and we're talking about the escape speed. And so the first thing to recognize is we dealt with the simplistic case of the circular orbital speed, and all that means is that it actually satisfies centripetal acceleration, centripetal force, and all of those relationships. But what happens now when our speed is actually less than the circular orbital speed or more than the circular orbital speed? And the answer is you get this different shape known as an ellipse. Now you'll notice that there is a small ellipse, which is when the speed is less than the circular orbital speed, but you also have this ellipse that is larger, and that's based upon the fact that it's going faster than the circular orbital speed, but it's not going so fast as to escape, so it's less than the escape velocity speed. And so now you have a different kind of shape that we have to talk about, which is the ellipse. And we're going to talk about that in a second. But the other two that I think that are worth noting is this is why there are certain things in our galaxy, in our solar system, around our planet that we only see once in a while or once ever. And that's due to these other orbits that we're talking about, which is a parabola and a hyperbola. And the basic idea you need to understand about these is the parabola is very much the classic shape that you've seen in grade 11 math or sooner. And the hyperbola is just a different conic section that is related to these other four. If you don't know what a conic section is, I would encourage you to take a look online. But these ellipses are something that's important. And there was a fellow named Johannes Kepler that was able to come up with his 3 laws of motion from it. And I usually go through a long history of astronomy and how we went from a geocentric to a heliocentric universe and how the orbits played a key role in that. But I'll save that for in class. Certainly I would take a look. It is a very interesting discussion to be had. But what Kepler found out is that there was this motion in the sky that couldn't be satisfied by circular orbits, specifically the motion of Mars. Mars does what's called retrograde motion, and that means that for a part of the year, it actually looks like it's going backwards relative to the motion, and then it goes forwards again. And what Kepler found out is that if the orbits are elliptical, then things like retrograde motion were very well satisfied by them. And so he created his 3 laws of planetary motion. And the first law is that planets are going to move in elliptical paths, and the sun is going to be one of the foci. Now, it's important to understand that there's a definition here of an ellipse based upon the major and minor axis. In math class, you would define it as x squared over a squared plus y squared over b squared is equal to 1, where b and a are the values of the major and minor axis. The key thing to note about this, though, is that this is an exaggeration. That the real motion of the planets are very, very, very almost circular. But the fact that they are a little bit elliptical is the reason why that over these grand distances of the solar system that we're able to see things like retrograde motion. The only planet that actually had a very elliptical orbit was the one that was since kicked out of being a planet, and that was Pluto. And it was certainly one of the reasons why we questioned its existence as a planet on its own. Now, there are 2 terms there, perihelion and aphelion, which are the nearest and the closest path to the sun. Those are worth knowing what those terms are and how they apply. But as far as the mathematics goes, not a hugely important thing to understand outside of the fact that it looks a bit like an oval. Now, Kepler's second law is stated in a bunch of different ways, but the key idea here is that if you take a point, say from A, and it's going at a speed to B, and you have a different point C, and it's going on a speed to D, those areas have to be swept in equal time, and they have to be of equal area. This is also known as the conservation of angular momentum. And the basic idea behind this is because the area has to be the same, because the time has to be the same by which the object moves from A to B and from C to D, that the object from C to D must be moving faster to incorporate more of the area as a result. And so the biggest thing to know here is objects that are closer to the sun are moving faster than objects that are farther away from the sun. So Kepler's third law states that the square of the sidereal period of a planet is proportional to the cube of its average distance from the sun. Well, what does this mean? Well, the Earth orbits around the sun, and when it gets back to its original position in space, because it's been spinning, it doesn't necessarily line up with the original background stars that it had originally. So the sidereal period is the time it takes to orbit around the sun and end up at the same background stars that it did before. When you talk about the synodic period, what we mean is the time it takes for the Earth to orbit around and end up to the same position relative to the rest of the planets. So although this is a nitpicky thing, it's not really important. You're only ever going to be talked to in this class as far as a period being just an orbital period, the end. And you can see that when we graph the cube of the semi-major axis and the square of the orbital period, what you see is this linear relationship, and this is really important, because this was really the final dagger in understanding that elliptical orbits were the way for our solar system, because it was such a nice straight line associated with Kepler's third law that it had to be the reason why certain motions were better explained using ellipses. So if we get into a basic derivation, and let's just assume that things are moving in a circular path. Okay, yes, I know we just talked about it in terms of ellipses, but we can do a derivation of Kepler's third law using circular motion. And the way we do that is to understand, again, that Fg is the only force causing its circular path. We know that V is equal to 2 pi r over t. When you substitute in and you do a little bit of algebra, you see that t squared is equal to 4 pi squared over gm times r cubed. That is exactly the same idea as saying that the period squared is proportional to the radius cubed. So folks, even using circular motion and using Newton's law of gravitation, we can still come up with a relationship that talks about period squared and radius cubed. So folks, gravitation is complete. It is a big part of the unit. It's an important part of the unit, but at the same time, it's all applying circular motion. It's applying things that we've already learned in previous courses. So hopefully most of it made sense. And the best thing you can do now is put your heads down and start doing some practice problems and try to make sure that you consolidate this conceptual understanding with some practice work. This concludes our unit on circular motion and gravitation, and best of luck to you with your review studies and any assessments that you may have.